The next topic that we're going to be looking at is reflection and stretches. A reflection is a transformation where the graph f of x is reflected about the x or y axis. In other words, it creates a mirror image about the x or y axis. Reflections are said not to change the shape of graph, but may change the orientation. For example, an upward opening parabola turns into a downward opening parabola when it is reflected about the x-axis. Here's the x-axis. Now, let's take a look at the gray parabola. If we reflect the gray parabola about the y-axis, what does it become? Well, it just really remains the same. So, let's move on. Reflections and stretches summary. So we're going to start off with transforming in words. We're going to look at the mapping notation or point notation, and then we're going to do an example. The blue is the parent function of each transformation. Let's start off with the first one. Y is equal to negative f of x. When it's y is equal to negative f of x, this is a reflection about the x-axis. You can think of this as, have you seen this before? Absolutely. Y is equal to negative x squared. So the negative is implying that it is reflected about the x-axis, and each point, x, y, is mapped into point x, comma, negative y. And that is, I take this point negative 3, negative 1, and it maps into 3, comma, 1. And we might have point up here that is defined as 2, comma, 4. But when we reflect it, it turns into 2, comma, negative 4, etc. Exactly how our mapping notation defines this. So this is a reflection about the x-axis. Now, if we have a function y is equal to negative f of x, well, again, let's start off with our function f of x. F of x is blue. So if we have y is equal to f of negative x, this is a reflection about the y-axis. Now, how do we reflect about the y-axis? Well, we have point xy, and that is transformed into point negative xy. Now, I'm just going to take maybe one point. This is 0.24 on my parent function. If I reflect this about the x-axis, the y-axis, it becomes point negative 24, right up there. And you can continue on and take additional points to convince yourself that this is true. Now, our next example, y is equal to a f of x. This is a vertical stretch about the x-axis by a factor of absolute value of a. So xy gets transformed into point x, comma, ay. So that is what we multiply the y values by a. We say that this is a stretch by a factor of a. Again, let's take this, for instance, y with 0.24. And what happens here is that this point gets stretched all the way up to 2.8. So this would be a vertical stretch by a factor of 2. Now, just for helping you along, here the value of a would be 2, that we're stretching it by a factor of 2. Now, we have y is equal to f bx. Now, if you notice, in brackets, the b is before the x, and it's somehow attached to the x. This is kind of bizarre, and it keeps with the theme that horizontal transformations are often opposite of what you think. So y is equal to f, open brackets, bx, close brackets. This implies a horizontal stretch about the y-axis by a factor of 1 over b. So if b is negative, you have to reflect it about the y-axis also. So let's just take a look. Y is equal to f bx, and we see that our mapping notation takes point xy and it maps it into x over b comma y. So in our example, we started off with 0.24 yet again, and we stretch it by a factor of, well, it's kind of weird. We say, now I'm just going to help us along by writing out the notation here. This would be y is equal to f of 2x. Now, we call this a stretch by a factor of 1/2. And really, what you're doing is you're dividing your x values by 2 or multiplying them by a half. We could also say we're compressing our x values by a factor of 2. My mistake. I think that I said y values there. When we're doing a horizontal compression, horizontal stretch, this is horizontal. Only x's move, not the y's. Pardon me. So here, b would be equal to 2 in this example. Now, that is really strange. We're going from blue to purple, but yet b is stretched by a factor of 1/2, 1 over b. Okay, moving on to this next example. Good times, I think. So, example, a reflection about the x and y axis. Given the graph of y is equal to f of x, so I'm just going to write y is equal to f of x. We're going to denote the domain and range. We're going to sketch the domain and range of this. So y is equal to f of x. Just for a frame of reference, the domain and range, I'm just going to write this down. Probably makes most sense in interval notation. Goes from -2 to 4, that would be the domain. And the range would go from 0 to 3. That's of my parent function. We're going to sketch the graph of the transformed graphs. We're going to write each in mapping notation, describe in words the transformation, and note the domain and range of the transformed function. Let us start off with a, g of x. Now, g of x is equal to negative f of x. So if we note that the negative is in front. So here, a is equal to -1. I'd like writing it out because it helps me settle up what I'm going to do. My mapping notation takes my regular point, xy, and maps it into x comma -y. My words would go something like this. We are reflecting in x-axis. Note the domain and range of the transform function. Well, I should really get down to business and write the transform function. I actually think this when I'm doing it. When I'm going to maybe take red to denote g of x. So I'm going to take this point right here, -2, 3. I'm going to reflect that in the y-axis. It becomes -2, -3. 0, 0 stays at 0, 0. That is, the y value is multiplied by -1. It remains the same. 2, 1 is transformed into 2, -1. 4, 1 is transformed into 4, -1. That is, in my point notation, really I'm just multiplying the y values by -1. There we have it. So my domain and range Well, my domain, if I take a look at the red graph, my domain goes from -2 to 4. My range changes, and it goes from -3 to 0. Now remember, this was a reflection about the x-axis. We multiplied our y values only. Our x values stayed the same. And if you note, our domain stayed the same. But it was our range that changed, because essentially we're just multiplying our y values by -1. All right, let's start off with h of x now. Let's look at the other one. So just to help us along, no, I'll keep it up. I was going to erase the red graph, but now I'm actually working off the gray graph again. So h of x is equal to f, open brackets, -x. So we're going to sketch the transformed graph. So I think what's important here is to recognize that there is a coefficient in front of the x, and that would be -1. Pardon me. And in words, or we take point xy, and what happens is that this is changed to point -xy. And what's going to happen is that we're going to be reflecting about the y-axis. So I'm going to be taking this point right here, this point -2, 3, and I'm going to be looking at this point notation. Essentially, what do? I multiply my y values by my x values by -1. So -2, 3 becomes 2, 3. Now I'm going to take this next point right here at 0, 0. What's going to happen is 0, 0 remains at 0, 0, because now if I multiply the x value 0 by -1, it remains the same. This next point right here, 2, 1, I'm going to multiply the x value by -1. It becomes -2, 1. Last but not least, the point 4, -1 becomes -4, 1. And I'm just going to connect the dots. There we have it. I'm just going to highlight our parent function just so that we can look at it. Now, I haven't used a ruler, which is unfortunate. I don't have a ruler on this thing. Anyways, if we take a look at the blue graph, the highlighted blue graph, it is actually a reflection about the x-axis. It becomes the red. But if we take the blue graph and we reflect it about the y-axis, it becomes the purple graph, or the reflected about the y-axis function. So I find this interesting in the domain and range. Of this, the domain of the purple graph, ask yourself, well, how did they change? If you take a look at the purple graph, the domain changed because really you were multiplying the x values by -1. And if it was -2, 4, and you multiply those x values by 1, it would be -4 to 2. The range, well, the range would remain unchanged because it was a horizontal transformation.